All right, so today I'm going to be talking about the client server model, and how that works in FPS games. In particular, how you can keep your your like camera smooth, because fundamentally there's a little bit of an issue, which is that in client server, your client can have a variable FPS rate, and that's because better computers get more and stuff like that. But also, monitors with higher refresh rates need to produce more information to take advantage of the um, the refresh rate, because like if your game only updates at 60 hertz but you're rendering at like 144 hertz, maybe like that'll make sense in a second, but if that's the case, then you are paying for the monitor and your game is not expressing enough information to take advantage of that. So that's actually that's not usually an issue in single player, but in multiplayer that is a bit of an issue. So specifically, let's write down what data we're talking about is going to be important here. So in our context, let's talk about like the camera. So the camera, we'll just write like this is the game state. So the game state is going to consist of the yaw pitch of the camera, and this will become more clear in a second, but it will also contain LMPX, LMPY. And what is that? Well, LMP stands for last mouse position, and that's kind of the API we're assuming. As the mouse moves around, you get a mouse X and a mouse Y position, and L is just standing for the last one, so like the last one we've recorded. And okay, so what do we do with something like that? Well, when a new mouse position comes in, so what I usually write is game state gets mapped to under a new mouse position, and a mouse position it's a tuple, so it's like mpx comma mpy, and that maps you to a new game state prime. And here we know that the game state prime is going to be another game state, but now the yaw is the initial yaw plus, and here we do mpx minus lmpx. So this is like the delta of the two mouse positions, and then we would write pitch becomes pitch plus mpy minus lmpy, right? Yeah, and then we replace the last mouse position with, so the last one we use is this one, so we use it here. And that's like kind of like the fundamental iteration based approach on how a camera changes with the mouse that produces like mouse positions. That's usually how we do that. There can be like a scalar, or like constant multiplying by the mouse delta term, which is your sensitivity. Let's just assume it's 1 for now. You can always like add that in and it doesn't change anything. And before we go any further, I want to prove a property about iterating on these game states with a bunch of mouse positions, which is an interesting thing to look at, and it's a telescoping property. So what I want us to look at is going to be something like this. So let's just say we have game state 0, and then we operate on it with MP1, and to produce game state 1. And that's this expression evaluates to the game state 1. This is just kind of like an easier way of writing it. And then on top of that, we apply mouse position 2 to produce game state 2, kind of bracketing that again. And then we'll do that over and over to produce game state n, where we used mpn on whatever the last one was there. So what I want to say is this is going to be the same as just starting at game state 0, applying mpn, and that gives you GSN. And the way we can see this is we'll do it like this. So instead of talking about yaw and pitch separately, we can kind of combine this operation if we vectorize some things. So what I'll just write is like, for this one, it has yp0, and yp0 is just like that tuple of yaw pitch. So what do we know here? We know that, I'll write larger here. So yp0, well, yp0 doesn't have much information. Yp0 is just y0, p0. And now, but what is yp1? Yp1 equals the previous plus, and then also we can write, I'm going to write lmp0 to be lmp0, lmpx0, lmpy0, which is like this data, but just for that first element. So what's going on here? So it's yp1 equals yp0 plus the delta, and since we're vectorizing it, it actually becomes easier. So what we write here is mp0, or mp1, sorry, because that's the first one, mp1 minus lmp0. And I guess like the L is kind of redundant, but I'll just leave it for now. Okay, so that's what yp1 equals. And what is yp2? So yp2 equals yp1 plus mp2 minus mp1, right? And so now we know yp1 equals yp0, plus mp1 minus, I'm just going to knock off the L. I don't really like that for now, just to keep things easier to look at. So mp0, so that's what yp1 is. Then we're doing plus mp2 minus mp1. And so here we can see the telescoping. So this guy is going to cancel with this guy. And so we can write this as yp0 plus mp2 minus mp0. And I'm not going to like do the formal proof here, but in general, what happens is, what you'll notice here is you see the 2, you'll get that here, and then it will also, every iteration will cancel with the previous term in that same way, or the internal terms will all collapse. And you can prove that by induction. I won't do it right now, but just know that you can. And so in general, ypi equals the initial yaw pitch plus mpi minus mp0. So once we know that, that's true for all of this. So that allows us to say that like ypn, which is the yaw pitch of this guy, ypn equals yp0 plus mpn minus mp0. Okay, so that's interesting. It's all collapsed down, and fundamentally, so your ypn, and then also for GSN specifically, the last mouse position X and last mouse position Y would be produced from MPN. It's kind of like excess information, but it's true. And what this allows us to say is that when you do GS0, and then you just do MPN, and then produce like a game state, I'll just write that. Then when you do this, so whether you do this or this, we can deduce that like the game state produced by just doing it on MPN is the same as when you iteratively do it. So these two things are the same. Okay, so that's a lot of work to just to say that. But the reason why this is so great has to do with how the client and the server interact. So, if I give us a client here, and these dots represent those game states we've been talking about. And the way you move from one game state to the next is by so yeah, I would just kind of map it like this. So GS0 is like that, GS1 is like that, and then these MPs are like what goes in between. It's like the arrows. So it's just a visual simplification to help us focus on what's happening on a client and server. So here's a client, and a server is doing the same thing but at a much slower rate. Okay, so that's a server. And you have GS0, GS1, GS2, and also up here we have GS0. And to denote the difference, let's just put a prime on all of the server game states. So with this in place, there would be, MP1, MP2, MP3, and so on. And so what's going on here? So at some point, we're going to send over some information to the server. And this is going to be in the form of like a mouse and keyboard update usually, but we're just talking about like camera, so it's just going to be mouse for now. So with a mouse update, it's just going to pass over MP3. So that's mouse position 3. And the reason why we don't have to pass over all this extra information is going to become clear, and it has to do with that thing that we just proved. And I'll also like just label the game states, so GS2, GS1, GS2, GS3. And what I want to say here is that I want to prove that GS2 prime is the same as GS3. So the one on the client is the one on the server. And that's an interesting thing because it's only operating on this data. So let's see why that's true. And just to recall, like, each of these have an initial state of being zeroed out. So their yaw pitch is 0 and their last mouse position is the 0 vector as well for both of them. In general, as long as they're initialized to the same value, which is what we kind of proved in the theorem there, about the telescoping thing, this following argument is going to hold, but they're just initialized to 0. So what's going on here? So how do we get from, so let's just write on the server, on the client, what do we have? We have GS0, MP1, GS1, MP2, GS2, and then MP3, and then GS3, right? And by that theorem that we had proven previously, this is the same as just doing GS0, MP3, and then obtaining like GS3. It produces GS3 if you start at GS0 and apply MP3 by the previous theorem. That's what I'm writing here. Okay, that's great. And because okay, right? That's step 1. And now let's see what goes on the server. So on the server we start with GS0 prime, and then something happens and we get GS1 prime, and something happens and we get GS2 prime, right? From GS1 prime to GS2 prime, what the server does is it will take that mouse position that was received and apply it. So it applies MP3. And since no data was received from GS0 to GS1, like this operation is completely optional. Like the way I like to think of that is in general, like since this is initialized with like the zero vector, then you could like also pass in the zero vector as like a mouse position, and it will not modify the state. So GS1 prime equals GS0 prime, and if I wanted to, I could like kind of write it out like this. Um, but yeah, so because GS0 prime equals GS1 prime, and we also know that like the start states of the client and server are equal, so we know GS0 prime equals GS0. Then we know that this is the same as GS1 prime, or yeah, so I could write GS1 or GS, so I could write this, you just do MP3 GS2 prime, so I could knock out that first part, it's not required. But GS1 is the same as GS2 or GS0, so this is also the same as GS0 prime, MP3 GS2 prime. And because we know the client and the server start with the same initial state, so this is GS without the prime, then I can replace that and get GS2 prime. So now because we know GS3 is just GS0 and you apply MP3, and we know GS2 prime is GS0, and you apply MP3, then this implies that GS2 prime equals GS3. So all of that work is just to show that after the first after the first information is passed to the server, on the next game state, it will be equal to the game state on the client at which it was sent. So we're kind of proving some sort of like fact that like these two systems are interlocked in a certain way. Now that fact isn't the most useful one that we're going to look at. There's a more interesting fact. So now we're going to kind of delve into client prediction and server reconciliation. I am going to assume you're a little bit familiar with that. So I will mention how it works though. So as you know, the server is authoritative in FPS games. So when the server sends a message back to the client, so let's just draw this here. It's gonna say what the last mouse. So you see this index on the mouse positions. It's gonna return the index of the last used mouse position. So here's gonna return number 3. Now in the client, these nodes here are the predicted ones. So what's going on is like there's more mouse updates. So MP4, MP5, I guess like MP6 would be there. And what happens is when we receive this update, and I guess we'll operate it on the next tick here. So when we get here, we need to reapply all of the mouse updates that have occurred on the client. So what do? We first on the client, we slap in. So the game state will also send like the yaw pitch that's on the server right now. And it will, because the server is authoritative, we initially just want to slap in that yaw pitch on the client because we need to keep it synchronized with the client. But in the meantime, like since that mouse update 3, there's been like 2 or 3 more updates that have happened on the client. And so if we were to just slap it in, it would totally mess up the camera. It would just like turn it at a weird angle, which is not what we want. So what we want to do is we look at that number 3 and we collect all of the mouse positions that were used to update the state since then. And then we apply those on top of the slapped in yaw pitch. And what will happen, hopefully, is that will not modify the currently predicted yaw pitch. And it won't modify it, as in like the produced value will not be different if the yaw pitch produced here was the same as GS3, right? And we know that is true because of this proof here. We proved that here. We proved that GS2 prime equals GS3. So this data here was literally just pretty much GS2 prime being sent over. So because we know that, then we know by applying these two on top, we're going to... So formally, what I'm trying to say here is if you have GS3, and I'll also label GS4, GS5, and maybe I'll just make some blank space at the bottom so I'm not cluttering stuff. So right now on the client, we know that the current state is we took GS3, we used MP4, and then we got GS4, and then we used MP5, and that gave us GS5. And I guess I won't think about MP6 for now just because it's going to simplify what I want to do here. So with these 3 in sequence, just like that, then we want this to be the same as if I slap in GS2 prime and then do those again. So MP4, GS 4 prime. So I'm just actually I'll use like a special like star up here because these are not going to be the same as, potentially not the same as anything else. These are like potentially new game states. MP5, reapply that one, and then GS5, and then star. So what I want to say is like that is equal to that. So this is like your predicted, and this is like the reconciled, because the reconciled uses the server state and applies them on top. But this thing here that shows us that GS2 prime equals GS3 shows that these are equal because this is the same as GS3, and if you apply the same sequence of events on top of it, you will obtain the same game state, right? So this is kind of like the base case. The initial fact that after like running it after receiving your first update, like these two things will be equal. And then this induction step is kind of like on every time you reconcile, because you have this fact that like the previous one equals the one you just sent over, then when you apply on top, the reconciled and the predicted state are the same. And then so that's kind of like the induction step. I'm doing it with concrete numbers because I don't want to like involve a bunch of different techniques when it doesn't require that to understand it. But this is like a proof of why this works. So, like reconciling occurs over and over, but as long as you have this property that like these two match, then no matter when it happens, you're reapplying on top of the same game state. And so the reconciliation will never have any error in theory. Obviously, dropped packets will change that fact, but in general, this proves why reconciliation in this manner will not have any error. So yeah, I think we're nearing like 25 minutes. That's pretty much the main part of this. And now the next part of this will just be talking about how this hooks into like firing weapons in a game in the same setup. So I'm going to keep this on the side if I want to reference it. Yeah, and I'll put this one in. So now, what does sub-tick firing look like? Because we've only talked about aiming so far. And now I want to talk about, like, well, there's a few things I do want to talk about. This video is going to get long, but I want this to be a reference. I don't really imagine anyone is going to watch this all the way through, but instead just kind of look at it when they need a refresher on it. So the first thing to talk about is, well, maybe I'll just kind of point at this for now. So as we know, the server sends updates to the client at like a slow rate, which we understand because like every time you're going to send out an update like here. So there's a lot of frames that are rendered in between game updates, right? And that's why we needed the prediction and reconciliation, is because we want to take advantage of those frames to make the game match the monitor's resolution. But you can imagine that this game state is no longer just where you're looking, like the simple yaw pitch idea. It would also contain like where your enemies are and everything like that, right? And also, let's assume you have a gun and you want to shoot those enemies, and it's like a hit scan weapon. So in these game updates, it will also contain the position of, let's just say, one enemy for now. Like there'd be more, but for our case, let's just simplify. So there's one enemy with a position, call it the target. And so on the screen, you're only ever going to see that thing update at this rate, which is like a very slow rate compared to how fast your camera is updating, because we just got the camera updating well now. And so we want to match it. And so what we do is we wait until the client has at least 2 game updates. So we're delaying the client's view of things. And then we interpolate between the 2 game states. So, you know, the target has a position here and it has a position here. And if we're here, then we can just say like how far are we between the 2 updates? So this would be giving us like a t value, where t is like a value between 0 or 1, which is how far we are between the 2. And I'll just get a cleaner drawing, I think, but for now, just so it's easier to understand. So what is subtick accuracy? So as of right now, what I just described is a way to move the target, the enemy's position, and I'll just continue drawing this. And let's say, send it a game update, send it a game update, send it a game update, right? So this is our server and this is our client. So here we send over our enemy's position, and then for each tick, for each time we render it, we can interpolate its position. But how does firing work, right? Because with firing our gun, how would that make sense? And also, like, let's assume we only send over at the same rate that so client to server will send at the same rate that server to client sends. I don't know if that's a good assumption, but let's just make it for now. So that will happen, something like that will happen, and something like that will happen. So with this, because, well, think about it. It needs to be kind of fixed rate. You wouldn't be, like, imagine you could send packets at the rate of, like, your refresh monitor. So someone with, like, 240 hertz would be, like, sending 4 times the bandwidth as someone on 60 hertz. It doesn't really make sense. It's better to kind of have that as a constant, I believe. But either way, you know, we're both sending back and forth at like a slow rate, pretty much. And so we can only send updates to the server then. And so, like, we can only really fire our weapon. So our weapon's resolution degrades. As in, when we fire the weapon, we can only know that we've fired, like, on that tick. Because, let's say, like, here, like, fire was not pressed. But here, fire was pressed. And what does it mean for fire to be pressed here? It means that, like, on either one of those subticks, the player, like, clicked the mouse and it was able to fire. And it means that, like, only here we can simulate the firing happening. And interestingly enough, I'm just going to write GS0, GS1, GS2, GS3, GS4, GS5, GS6. Okay, so let's just say, like, we fired on this tick, right? Before we had entity interpolation, our game state in terms of just the position of the target would only update when we received the new target's position. So it would be identical until, like, here or on there when we lock it in. And so when we fire here, we were shooting at the target at that time, right? So on the server, we would, in the packet that's sent, we would also say, like, when we fired, what was the game state? Like, what was that index? So we could say, like, the game state was 2. So then on the server, we can go back to, so on here, I'll write some game states. So, okay. When we sent this over, we were at game state 1, and so on the client, we were looking at, like, the target's position at game state 1 prime on the server. And we're going to store that. That's when we fired. That was the last game update that was applied when we fired. And so we will pass back 1, which is the index here. And so on the server, once we know that we've fired, we will revert back to this state so that the target's in the right spot, and then do the firing, right? And that will correctly, like, put the target in the right position. Okay. So there's that. But we also need to put the yaw pitch back to the right position as well. Because, at this point in time, so if we didn't have this prediction reconciliation system and being able to aim in subticks, then we wouldn't have to do this. Because the yaw pitch would, like, stay the same throughout, and so we could just simply, like, revert it back to the yaw pitch at game state 1 prime here. Or the yaw pitch at this state, I guess. Okay, it's complicated. That's why it's taking me more time to explain these ideas now. But fundamentally, let's just say, like, you get a time. So yeah, here is when we received the last game update, and here's the next time we received the next game update. So we have we have, like, a t value, which is, we're gonna say, like, a value between, like, 0 and 1, representing how far we are between those two ticks. Yeah, so we have that going on. And so when we fire, we can record what this t value is. And that will give us a way, and we will pass that t value along to the server. So we're going to say we fired, and we fired at the subtick position t, which is, like, within 0, 1 range. And then all that we have to do is, on the server, we would find whatever those two consecutive game states were, and then we can interpolate up to time t, and move that target. So now we're talking about just the target. We move its position to the right place. So now we have a way of moving the target to the right place on the server side based on what subtick position we were on the client side. And now the one issue is we need to be able to get the yaw pitch to whatever it was right here, right? And now comes the question of how we do that. Okay. I need to think about that for a second, but I think I can solve that on the spot. So maybe let's zoom in a bit, because I think this is getting a bit too large. So let's just say there were more than what I had written there. So this is within a subtick. And this is kind of like when the next tick happens. So these are the two ticks, and this is like the subtick. And let's say we fired right here. And we get a t value, which is between 0 and 1, representing how far we are between the two ticks. Yep, that makes sense. And then also, we just have to remember what's going on here. So, there's like a GS, and I guess I'll write 1, or maybe I'll write L, and a GS L plus 1, and a GS L plus 2, and a GS L plus 3. So I just want to say that that's an arbitrary game state, and we have sub game states, which are subtick game states on the client side, which don't really exist on the server, but they are produced when there's when there's like an MPL plus 1, an MPL plus 2. So you're processing these mouse positions L plus 3, and so on. Okay, good. This is good. So when we send when we finally send our we fired here, and this is the server sending us data, and we'll send back to the server. Let's just say we send back right here, and we're gonna tell the server yes, we fired during this time. So fired is 1, true or false. T is, I don't know, I'll just say 0.45. And the last, and let's just say the server sent over yeah, I guess I do have to draw a bit of this. So let's call that GSK prime, and this is GSK plus 1 prime, and this is GSK plus 2 prime. So we send over F1 and T of this time, and also we send over what the last slapped in game state from the server was. So we also send over I don't know what I'll call it, but we also have to send over K. Yep, this is all good. And then on the server, what happens? So we're going to have to send over more information. So right now we're trying to determine what extra information needs to go over to get the yaw pitch to the right place. So the server has to keep track of this information. It has to keep track of the game state in terms of the camera. So recall before we denoted the game state before. It's going to have more information than this, but it contained yaw pitch, and then it also contained last and mouse position X and last mouse position Y. So on the server, we need a history buffer that will store each of the game states' camera reconstruction information. So what we're gonna do now is we're gonna use we're gonna reuse the telescoping property that we used to prove something earlier on, but now we're going to do it on subticks, right? So let's just think about this for a sec. Just got to think. So actively in a subtick, we are equal to the server's game state. So we slap in game state K, and then we run subsequent like things on top of it, right? Might be like the reconciliation part to get to where we are right now. And so our current game state right now is going to be GSK prime, and then you use MP L plus 1. Sorry, that's pretty small, but I'm just saying like apply that, and that. Actually, you know what? No need to be small when I have a new page. So we have here, so it came from the server state. So GSK prime, and then we applied MP L plus 1 to get GS L plus 1, and then we applied MP L plus 2 to get GS L plus 2, and then we applied one more MP L plus 3 to produce GS L plus 3, and this is like the tick where we fired our gun. That's the game state where the gun was fired. Now, by the telescoping property, the state produced by doing this, which is the final state, is the same state as if you were just to start at GSK prime and then do MP L plus 3, and that would produce the same thing, so GS L plus 3. So because we know that, then on what we need to send over in addition to the firing and the subtick percentage is also the just the previous mouse position before we fired. So we also just have to pass MP L plus 3, because on the server we can produce the correct camera's state by taking GSK prime, and we know we can obtain GSK prime because we passed along the K index. So we revert our camera state to that, and then we apply MPL plus 3, and that gives us GSL plus 3, which is the subtick camera's game state on the client. So once we do this, then our aiming is we are subtick aiming correctly. So our camera is in the right place. So now that we have this, we combine this idea with the idea we had mentioned back here, which is how we interpolate our entities, or like our target, right? So we move our target to the right place based on where we had fired, and that uses that T value. And then we move our camera to the right place, but we don't use the T value, we use the previous mouse position applied on the like game state that was last applied on the client. And then we do that, and we get the right aiming, and we get the right enemy position, and therefore it should match with what we saw on the client, and it should work. Yeah, that's what I wanted to say. So yes, this was a long video, but there's a lot of information required to know this stuff works. Like, I don't think I could have made this system confidently without knowing all of that in entirety. It's definitely like an incremental knowledge thing as you go. But yeah, like literally you want to make a game, and so you want to take advantage of the monitor's refresh rate. And without doing all of that, you can't. You can't aim properly. You can't have accurate hit scan weaponry without knowing all of this. So, I mean, it can be accurate, but it won't be like, you won't be taking advantage of the resolution of your monitor. So I just wanted to say this so it's a reference for me or for anyone who's interested in making multiplayer FPS games with high precision and taking advantage of everything. So yeah, that's about it.